Hi everyone and welcome back. So today I wanted to continue by going into some examples of what we discussed in lecture. Okay, so the first example I have here is calculate the angular velocity of a 0.3 meter radius car tire when the car travels at 15 miles per second. Okay, and that's about 54 kilometers per hour. Okay, so what we're going to do is again, calculate the angular velocity. Okay, so first things first, my radius is 0.3 meters. Okay, and I have some kind of regular velocity. Okay, I'm saying that the car travels, right? And when I'm saying regular velocity, I really shouldn't say that. My tangential velocity or my linear velocity is 15 meters per second. Okay, so these are my knowns, and I'm trying to find out my angular velocity. Okay, so I'm going to go over to my PowerPoint now, or you could use your textbook, whichever one works. And I have this relationship here where angular velocity equals linear velocity divided by some radius. Okay, so this is what I'll be using. All right, so I'll plug everything in. I have 15 meters per second divided by 0.3 meters, okay? And we would get 15 divided by 0.3 is 50. Oh, come on, pen. 50, let's see. I would say radians per second, okay? So this is what is a little bit tricky when we're looking at angular velocity. Okay, remember that we're looking at a rate of change of some angle, okay? And remember how our delta theta, or our change in angle, or we called it rotation angle, right? Excuse me. That is measured in radians, okay? So I kind of just added in that radians. Okay, the radians is a little bit tricky, okay, because it seems like it is like not a unit really, but it is because it's some kind of angle, okay? So that's really tricky, so watch out for that. So just remember when you're looking at an angular velocity, it's going to be something in radians per second. Okay, so just be careful with that. Okay, other than that, this is a pretty simple one, very straightforward. Okay, so we're going to go ahead and move on to our next example. And this one asks, what is the magnitude of centripetal acceleration of a car that's following some curve here, okay, with a radius, I'm going to write that down, radius of 500 meters, with my speed v. Remember, when it's just saying speed and it's not saying centripetal or angular velocity, that is just our linear speed, our linear velocity. Okay, it is 25 meters per second. Okay, and let's see. We are trying to calculate, again, the centripetal acceleration. So again, I'm going to go over here to my PowerPoint and find that equation. Okay, so my centripetal acceleration, let's see which part we want to use. So we know our linear velocity, not our angular velocity. So I'm going to use that first portion here where it says v squared divided by r. Okay, and then I will plug these in. So I have 25 meters per second, square that, divided by my 500 meters. Okay, so I get 25 squared over 500. And I end up with an acceleration of 1.25 meters per second squared. Okay. Now, so that is our centripetal acceleration, okay? Now I want to compare that with the acceleration due to gravity, okay? So remember our acceleration due to gravity, I'm just going to label it that way, is 9.80 meters per second squared, okay? So if I want to compare that, I could say AC divided by AG, and I would plug those into my calculator. Okay. And I get 0.128 approximately. Okay. So this acceleration, this centripetal acceleration, is only 0.128 times the acceleration due to gravity. Or you can also think of it this way. You can say that it's about 12% of the acceleration due to gravity, if you'd rather think of it that way. Okay, but that's what we are looking at here. Okay. All right, so moving on. Again, that one wasn't too bad. Okay. So now we are going to do the same thing. We're looking at centripetal acceleration. Okay. And we're looking centripetal acceleration of a point that is 7.5 centimeters from the axis of a centrifuge. Okay. Now a centrifuge, maybe some of you guys have heard of it. I'll just briefly kind of describe it. It's just something that rotates like samples, and it kind of separates whatever, I'm not really sure exactly because I'm not a chemist, but I remember doing this in like Chem 1A, I think. We did a centrifuge thing, or maybe it was Chem 1B. I don't remember. It's been so long. But it separates some kind of chemicals from each other. But anyway, and so it's physics related, but little. So anyway, we're just going to look at this example here. So we have that some radius is 7.5 centimeters. I'm going to go ahead and convert that to meters. Okay. So we just divide by 100. Oh, I think I have too many zeros. I do. Okay. I got carried away on the zeros. Okay, so that's my radius. And I have that it is spinning at 7.5 times 10 to the 4th revolutions per minute. Okay. So what is this in revolutions per minute? That is actually going to represent our omega. Okay, so our omega, again, is typically in radians per second. So we're going to have to do a few things to translate this into radians per second. Okay, so watch out for that when you're going through the homework. You will have to do this a few times as well. Okay, so if I want to convert my 7.5 times 10 to the 4th revolutions per minute, okay, the first thing I want to do is convert my revolutions. Okay, so, excuse me, when we are looking at one revolution, say we start here, we go all the way around back to this point again. How many radians is that in one revolution? How many radians if I go all the way around the circle? It's 2 pi radians, right? We talked about this in the lecture. So what I will do is I'll say for one revolution, there are 2 pi radians. Okay, so now I have that first part figured out. How many revolutions per radians? Okay. Now I need to know to get from minutes to seconds. Okay, we know that in 1 minute, there are 60 seconds, right? Okay, so we will grab our calculator and multiply this out. Okay, whoops. So I get 7.8, let's see, 7.9 times 10 to the 123. Okay, and again, this is now in radians per second, okay? All right, so again, we're not done. That was just one little portion of this problem, okay? So now we have r and we have omega. We want to know our acceleration. So my acceleration is going to be r times omega squared. Okay, so I plug in my r, that's going to be 0.075 meters. Sorry, that's a 0. Times the 7.9 times 10 to the third radians per second squared. Okay. So this number is squared times 0.075. That gives me 4.6 times 10 to the 6 meters per second squared. Okay. So this is my centripetal acceleration of this centrifuge, or ultracentrifuge as it says. Okay, so at this point, I'm gonna go ahead and stop, and then we'll come back next time with some more examples.